Okay, the Argand diagram. The Argand diagram is a means of geometrically representing a complex number. And so rather than an xy axis, instead we now have a real axis and an imaginary axis. And it's really just a number plane, and this will be called the complex number plane, referred to as that as well. So the complex number plane, if we take a complex number, z equals x plus iy, then we can represent that as the ordered pair xy. And then I can plot its position anywhere on this diagram, which becomes, as we'll see later on, quite useful in terms of operating with these numbers as well. So for example, if I take z is the number 3 plus 4i, then as an ordered pair I'd represent that as 3, 4. 3 on the real axis and 4 on the imaginary axis, and that's my z there. If I take a separate complex number, w is equal to negative 2 plus I, I'll represent that as negative 2, 1, 1 being the imaginary part, and again just negative 2 and up 1, and there's w. So that's just a nice visual representation of a complex number, thinking of it as its real part and its imaginary part and plotting onto a plane. So what I want to look at now is how else we can locate a position on a plane. So we've talked about the real and imaginary axis and what we're used to, a Cartesian format, an x and y. I also want to look at another way of locating a point on a plane, or in this case a complex number on the plane, and that is by calculating the distance it is away from the origin and calculating the angle of rotation from the x-axis. And I call these two things the modulus and the argument. So the modulus of z is what I've written here, and that's the distance. It's the distance of z from the plane. You'll often see that written as r. You may even see it written as the modulus of x plus iy. And to calculate that, we just form this right-angled triangle here, and we know it's across x and up y. And we've got a right-angled triangle. Pythagoras' theorem tells us that this would be calculated by taking the square root of x squared plus y squared. The other component would be the angle, and so that's what we call the argument of z. So the argument of z is the angle taken of rotation. And so in this case, to calculate the argument of z, so that we call that theta, again, right-angled triangle, we just say tan theta is equal to y over z. And so I can actually locate any point on the plane by saying it is a unique distance away and it's a unique angle of rotation away. And that's, using modulus argument, that's what we call polar coordinates. Now I don't really want to focus too much on the polar coordinates right now. What I want to look at is how this lets me express a complex number in a different form. Because if looking up here, I'll call that r, modulus of z is r. Then I have a right-angled triangle here, and so in the right-angled triangle I can see that cos of theta is adjacent over hypotenuse, which would be x over r, which leads me to that the x would be equal to r cos theta. And similarly, sine theta is y over r, leading me to y is equal to r sine theta. And so I can then consider the x plus iy instead as r cos theta plus I r sine theta. That's x and that's y. And so now I'm writing x plus iy in terms of this modulus and argument, and I call this the mod arg form. Now I can simplify this mod arg form down a little bit by going, taking common factor of r out. So just making a note, this is the mod arg form here. So a simplified version of take common factor out. And then an abbreviated version of this is actually not to write the full cos and sine out and just say, well, it's r, and I've got a cos, and I've got an I sine theta in there. So I get this format. r cos I sine theta as an abbreviated format of the mod arg form. And we'll find out later that the mod arg form is quite a useful format for expressing complex numbers and then doing calculations, multiplication, division, raising to a power. This is quite a useful format for those. Okay, so here's a little example of how this works. Express 1 minus I in mod arg form. And so I'm going back and I'm thinking, well, the modulus of 1 minus I is the square root of the x squared, 1 squared, plus the y squared. And that just becomes root 2. So in other words, it's located root 2 units away from the origin. Then I need to get the argument. Now, before I do the argument, I always like to know where is this point located. So 1 minus I is located in this fourth quadrant. So I know then that the argument could be thought of as being this angle around here. Alternatively, the argument could also be thought of as this angle in here. And they're both arguments. This angle here, which is less than 180 degrees, the smaller angle to get to it, is what I call the principal argument. And so the principal argument is the one I'll normally head for to try and work out what the argument of a complex number is, that one that's less than 180 degrees. So I could find that by finding this full one and subtracting from 360. Or perhaps, as it works out, tan theta is how we calculate an argument, and we get there is y, negative 1 on 1. So I get that tan theta is actually equal to negative 1. Now I know tan was going to be negative because it's in this fourth quadrant, so the negative 1's highlighting me to the fact that it's in the fourth quadrant. So then I just have to consider tan theta equals 1, and that's an exact value, so that tells me that theta is 45 degrees, but now we're working in radians, so I'm going to call it theta is pi on 4. But because it's actually not pi on 4 is up here in the positive, it's got to be down in the negative quadrant, I can say it's negative pi on 4. It's negative 45 degrees. And that would be the principal argument down around here. The other argument would have been around this way, 315 degrees. There would be many arguments make up there. Just keep adding 360 to the 315 and every time you'll end back at the same point. But this is the principal argument, so this is the main one I want to use. So to express this in mod arg form then, the mod arg form is r cos I sine theta. So that would be r is root 2 cos negative pi on 4 plus I sine negative pi on 4. And in that abbreviated form would be root 2 cos I sine negative pi on 4. Okay, here's one where I want to work backwards and express it, not in mod arg, it already is in mod arg form. I want to take it back to Cartesian form. So I want to expand this, and I want to write this not in the short form, but in the longer form. It's 4 cos pi on 3 plus 4I sine pi on 3. And then I just want to use my exact values in the triangles here. So I just went pi on 3 means 60 degrees. So that's down here, pi on 3. My triangle is 2, 1 and root 3. And I can see that the cos of pi on 3 is a half. So I've got 4 times 1 half plus 4 times, now sine of pi on 3 is root 3 opposite over hypotenuse 2. And there's an I in there as well. So 4 times a half is 2. This will give me 2 root 3 I. And that's it in Cartesian